So, hello everyone. I had a request to do some more STEP, in particular from the late 90s, STEP 1 papers. And I started looking at it today, in particular the 1998 paper. This, what you see on the screen, is 1998 paper 1. Excuse me. And yeah, so I've tried the first couple of questions, and as usual, I'll run through the answer. In this case, I'll do question 1, and I'll try to remember to find some particular useful, how to say, training or some useful concept that can help you to answer STEP questions in general with any particular example that I look at. So I've left this question 1 on the screen here for a little while. If you want to obviously do it yourself in advance of watching the video, now would be a time to pause the video or stop it and come back later. So I'll just quickly read it. How many integers between 10,000 and 100,000 inclusive contain exactly 2 different digits? And they give examples 23332 and 12331 as satisfying the rule, and the example 33333 as not satisfying the rule. Obviously, we note the word inclusive means that we have to consider the numbers 10,000 and 100,000 as well as all the numbers, all the integers in between those two. Right, so that's the question. It's a very simple one in terms of its wording, and it's of a type that you'll see quite frequently at the beginning of a step 1 paper. We could call it a counting problem. Sometimes these problems are very tedious, I guess you could say, but they don't use any sophisticated concepts, so they have that advantage. It's a little bit difficult to tell immediately, unless you have a lot of experience, whether it's going to be easy or difficult, whether it's going to involve a lot of separate cases, or whether it's going to involve just maybe 1 or 2 clever tricks. So let me just note the bounding numbers here. So we're going from 10,000 up to 100,000, and we're considering, we're looking to count all numbers which use exactly 2 distinct digits. Right, so how do we approach this problem? Well, the first thing that occurred to me is that I know that any number that, how to say that, we're dealing with 2 different digits, so 2 different or distinct digits, and both of those digits have to be in the set from 0 up to 9. Well, obviously that's what a digit means, but in decimal, but so it means the numbers from 0 up to 9, so 10 different numbers are involved. And as you probably know, when you're doing counting problems, you have to but you can use the kind of mathematical constructs you can use involve combination, sometimes written like this, for example. 10 choose 9 would mean choose 9 objects from 10, or 7 choose 3, choosing 3 objects from 7, and I'm sure you know how to calculate that. As well as P permutations, where we don't just choose objects, but we count the number of ways in which the objects can be arranged. So I might write 7p3 instead of 7c3. Another kind of useful mathematical construct for counting is just powers. For example, if I have a coin, how many different possible sequences can I get from flipping the coin 3 times? Well, there's 2 different possibilities on the first flip, 2 different possibilities on the second flip, and 2 on the third. So in that sense, it's a power where the number of times the trial occurs is the exponent, the power, and the number of different possibilities on each turn is the base there. So those are kind of 3 mathematical constructs that can help in counting possibilities. I suppose those are the main ones, so maybe I've missed something. And of course, more generally, we need to use the concept that in order to find the total number of cases, you would need to add the cases that can arise according to different conditions. So it's pretty much always in this kind of problem about splitting the problem up into different subcases. But here, yeah, so to come back to this specific problem, again, to remind you, if you're not looking at the question right now, the question is asking how many different numbers can we construct using exactly two distinct digits, not two or less, but exactly two, within this range from 10,000 to 100,000. So if there are two distinct digits, then it should be obvious to you first of all that we don't really need to consider, let's say, this case. Have I got that right? Yeah, that's 5 digits. We're looking at 5-digit numbers here. We don't need to consider this case as different from, let's say, this case. It's the same situation, except that we've chosen two different digits to start with. So that already gives us a clue as to one part of the answer. One part of the answer is to say, well, we can choose using the formula NCR, right? So we can choose 2 objects from 10, where the 10 objects are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And of course that gives us 45 different choices there. So we choose 2 different digits. Notice that the differentness, the distinctness is implicit in the C notation. Yeah, if I've got 5 pens and I choose 2 from 5, it's not meant to include the possibility of choosing the same pen twice. So we've chosen 2 distinct digits. There are 45 ways to do that. Now you may be alert to the possibility that if one of those digits is 0, that might cause us a problem, because a 0 at the front of a number is not really a part of the number. Can look at it different ways, but you know what I mean. So we will address that issue in a minute, but you know, that's the kind of thing that can trip you up a little bit. You know, you have to break it up into cases, but I advise you to look for the simplest possible way to construct the object first, and then consider exceptional cases. So this much is clear. Now the question becomes, if that step has already been done. So suppose we chose 7 and 9, and remember, order does not matter in a choice, in a choose NCR case. Suppose we chose those 2 numbers, 7 and 9. We're now faced with the problem of counting how many different valid possibilities there are. For example, one valid possibility I've already given here, let's use a different color for this, is 7. Shall I use commas? Is that necessary? I don't think so. That's one valid possibility. However, this is not a valid possibility. So if we were to list all the valid possibilities, how many would there be? Let's just write one more here. That's another valid possibility. How many valid numbers are in that list if we've already chosen 7 and 9? Because obviously my idea is that, having counted that number of valid possibilities, I merely have to multiply it by the number of different valid choices. They're independent choices, aren't they? First of all, we choose 2 digits, then we choose the particular arrangement of the digits to form a particular number, satisfying the rule that both digits occur. That's really the rule, isn't it? Simply that both digits occur. So how many different possibilities is that? Well, I hope you can notice that the best and most elegant way to count that is simply to consider how many choices there are on each of the 5 digits. How many different numbers can we choose for the first digit? The answer is obviously 2. How many how many can we choose for the second digit? The answer is obviously 2 and so on. Oops, 2 for all of them. Now you might say, hang on a minute, you can't choose 2 for all of them because, well, what if they end up all being the same, right? It's like you're flipping a coin 5 times. If you flip a coin 5 times, it can come up heads every time. Now there's only a 1 in 32 chance of that, but it can happen. So we can't simply call that the final answer. Now maybe you could easily forget that well, it might be a bit dumb, but you could easily forget the fact that by counting all those cases, you're including 99999 and 77777. But I'm going to address that in a minute, like what can you do to avoid a mistake here? But if you notice that, which you probably would, then you should subtract the possibilities which are not valid, and the possibilities which are not valid are obviously how many? 2, right? These 2 invalid cases are the same number repeated 5 times. So what we've written here is the formula 2 to the power 5 minus 2, and we said to ourselves, this must be right, this must be the correct number of valid numbers using the digits 7 and 9 specifically. Now for my kind of meta comment in this video, my kind of side comment. And let's suppose, I don't think that's actually very difficult to believe and just say, okay, that's right. Well, let's say you were a little bit unsure, or the problem was a bit more difficult, and you weren't 100% sure you'd counted in the right kind of way. Is there any kind of checking mechanism you can use? This is a big problem in exams generally, and certainly in STEP exams, is if they're not giving you a final answer. I should have mentioned that actually. They don't give you the final answer in this question. That would be enormously useful. So the fact that you don't have a final answer creates a difficulty, which is there any way we can check? I mean, we can't fundamentally check, we don't have the final answer, but we can do something, and we can use a method which I think is extremely common amongst mathematicians. I mean, I'm not a professional mathematician by any stretch of the imagination, but of course I've met people who are, and I've seen people do mathematics, in person, in books, and goodness, I don't know, lectures and so on. And so from my general experience of mathematics and mathematicians is this technique is incredibly widely used and incredibly valuable. Now, what is this technique which I'm overhyping? The technique is to create a toy problem. That's one way to write it. Create a toy version of the problem. And what that really means is simplify it down. It could be reduce the dimensionality, well, yes, that maybe is a good way of putting it. In most cases, reduce the dimensionality of the problem by reducing the number of variables somehow, or by reducing the size of a particular counting variable. So in this problem, we were dealing with the numbers from 10,000 to 100,000, which is basically all 5-digit numbers plus the final number 100,000. Which means that we can't count one by one. But what about if we were to make a somewhat toy version of the problem, where we were looking at the numbers from 100 up to 1,000? Okay, we still could conceivably get this wrong. I could reduce it to 10 up to 100, but I think when you get too small, it might be difficult to see the patterns. So that's just my kind of intuition at work there. I mean, you might not see it like that, but it's certainly the case that if we can understand the correct pattern for this lower level problem, it can give us a little bit more confidence in whether we've got the correct pattern for the higher order version of the problem. So in this case, suppose again that we just chose the numbers 7 and 9, because the first part of the logic, this idea of choosing two digits out of the digits 0 to 9 is still the same. What's different is that the number of cases that we're going to deal with is much smaller. So if I were to write down all 3-digit numbers using 3-digit numbers using 7 and 9, I mean using both 7 and 9. The whole point is that we have to use both of the digits in the number. I mean, it's pretty easy to see that's a pretty short list. Let's start with 7 on the front and see how far we get. 777 is not valid, but 779 is. 797 is clearly valid. And 779, 797, are there any more? Oh yeah, of course, 799, there we go. But that's it, isn't it? If you look at these three cases, we can't find anything else starting with 7. The only other possibility would be 777, and that's not valid. And then, of course, we've got the mirror image. We've got the same thing just reversed. And so we can easily see, and it's something we can fit into our brain, there are 6 possibilities. Now, does this fit in with the given formula, or the sort of say deduced formula for 5 digits? We got 2 to the 5 minus 2. Well, yes, it does, because this is 2 to the 3 minus 2. In other words, it's 2 possibilities times 2 possibilities times 2 possibilities, and then subtract 2 for the 2 cases, 999, 777. So I apologize if that was all very, very obvious, but I was trying to find an opportunity to explain this concept that, in my opinion, is very useful in certain specific cases to reduce your difficult problem to a toy, simpler problem that you can map out very explicitly without taking ages, right? Because it would take ages to write down all the 30 different possibilities for 5 digits. So obviously this is not intended to be part of your actual sort of exam sheet answer, but I'm just making some more space on the page here. But yeah, so I'm just going to save this. Save that. So yeah. I'm sorry, I totally lost my train of thought. Okay, so we've verified that we get a structure, or we get the number 2 to the n minus 2, and probably we didn't need to, but we did it anyway. Okay, we haven't finished the problem, have we? What we've deduced so far is something like this. Let me write it out explicitly. So far, what do we know? Given 10 digits, we have 10 choose 2 times 2 to the 5 minus 2 possible 5-digit sequences using 2 digits. Let's say using both, to be explicit, of 2 digits. And we can write down exactly what that is, but it's not the final answer. So why is that not the final answer? Well, very simple. The problem with that calculation is it includes numbers which start with a 0. For example, this. Have I gone too far? Yes. So this is not a valid solution to the problem because it's not actually a 5-digit number. Actually, that specific case is valid because it's no, hang on a minute. No. We start from 10,000, we go up to 100,000. Right, so this is not valid because it's actually the number 1,000, which is less than, what were we saying? 10,000, yeah. So we don't want numbers which start with a 0. So how do we, well, let's write down the number we had before, 10C2. So 10C2 times 2 to the 5 minus 2, let's simplify it now, equals 45 times 32 minus 2. 45 times 30, so what's that? That's 450 times 3. 1,200 and... hang on a minute. 45... Oh, it's 1,350, isn't it? Yeah. Sorry, I'm a bit slow and I don't have a calculator. But anyway, it's too big. So this is too big. Now then, how do we remove the numbers that we don't want? So we want to know how many numbers of form how many numbers in this set are of the form 0, let's say x, 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 x. I don't mean that they're all the same digit, I just mean they're 0, leading 0. But also in this set. So in other words, I don't want to count all numbers that start with 0. I want to count all numbers that start with 0, but which also were in that previous set. So how do I do that? So in other words, I want to count everything that looks like 0, 1, 0, 1, 1, for example. But I certainly don't want to count 0, 1, 0, 3, 2, because that was not in the set that we calculated with this formula, which were numbers including only pairs of digits, right? So let's not so in these cases, so I'm going to remove that because that was not included. So let me give you another couple of examples of what was included, right? 0, actually it would also include things with 2 leading 0, 0, 8, 0, 8, or 0, 9, 9, 9, 9. See, so anything like that. So in these cases, you can understand. Let's just use black. In these cases, the pair included 0. So it was 0 and another digit. Now, of course, the other digit has to be different from 0, otherwise it's not valid. So how many different possible pairs are there? Clearly there are 9 pairs now. In other words, it's not 10 choose 9 choose 2 anymore. It's 9 choose 1, which is just 9. And given that we have made that choice, then we're looking at the same problem as we had before. In each case, we have to choose one of the pair of the digits. One of that pair is 0, and the other one is another number in the set from 1 to 9. And there are four places we have to choose. So it's again the same pattern: 2 choices on the first digit, 2 choices on the second digit, 2 choices on the third digit, 2 choices on the fifth digit. What did I just say? There's 4 digits here anyway, because the 0 at the front is fixed. However, here we have to subtract. Let's think about this. We don't want to include the one case which we didn't include before. Remember, that's why I underlined in this set. I guess that's the only final tricky point in this problem, is just make doubly sure that the stuff that we're going to subtract from what I've underlined in red above here. Sorry, just do that. Yeah. So the stuff we're going to subtract from the number 10c2 times 2 to the 5 minus 2. I've just changed this so I can make nice underlinings now. There we go. We're only going to subtract from that things that were already included in it. We don't want to subtract from it things that were not included in it. So, if we consider the case 09999, was this case included in that count? Well, the answer is yes, because when we subtracted 2 in this formula here, we were subtracting forms where there were 5 consecutive digits the same, such as 99999 or 00000. So we did not subtract there the case 09999 because that did fit the formula of using both digits at least once. So we will have to subtract cases like the one I've just marked with an arrow here. So for any particular digit that we choose out of the 9 digits 1 to 9, so just in this case I chose the digit 9, we're going to count all the possibilities by multiplying 2 together 4 times, but then we're still going to have to subtract the case that was not included the first time round. Sorry, what am I saying? I'm confusing myself now. So we need to subtract one number here. I hope that's clear, is it? Let me think. That was not included. 4, 1. Oh, that was it. Yeah, I've remembered now. Sorry. Yeah. So yes, it is quite confusing actually. So the case that we are subtracting here, maybe it's not obvious from what I've said so far. So maybe it's a good little puzzle for you. Why am I subtracting 1 here? Well, the answer is, if you consider that in this formula is accounting for all cases where we've got a pair of numbers, 0 and another number, let's say n. And so the n refers to the 9 there. There are 9 possibilities for n. The number of possibilities is 2 to the power 4. There are 4 digits. But remember, that's including the possibility of 0, 0, 0, 0 for those 4 digits. And that's the possibility which we did not count before, because this 0 here on the front gives 5 zeros, and that was not counted before because it was included in this subtraction here. So that's why I subtract 1 here. So it's to remove the case 0, 0, 0, 0, 0. Alright, so that removes that case. So the total number of cases that we have to subtract from the previous number to get the right answer is, now what's that, 9 times 15. So what's that, 100 and, oops, not 5, 15. 90 plus 45 is 135. Okay, nearly finished. So we have the number 1350. Total cases which are valid is the 1350, subtracting all the cases which are included in that set but start with 0, which is 135. That takes me back to 1215, but I have to add one more case. And which case is that? This is the case 100,000, which was never included in any of our calculations because it's a 6-digit number. But it was included in the question because the question said inclusive. Okay, so let me just double check that gives the right number. So 1200 plus 15 plus 1, yeah, equals 1216, which is I believe, the right answer. Okay, so I hope that was helpful, and I hope the visuals come out clearly on the video, because this is a slightly new setup, and I shall probably be doing question 2 on this paper very shortly. So speak to you again soon. Bye bye.